These ones on the right, including saliva, the engine oil I talked about before, putty, molten plastic, these are non-Newtonian. These all have nonlinearity in those curves. And the mystery is why the molecular ping-pong balls, the dense suspension, why is it ever non-Newtonian? Because the first pass theory seems to constrain it in such a way that it must be Newtonian. So that's part of the story I shall try to tell you. So, it looks like I'm getting through this talk very quickly, doesn't it? Unfortunately, I'm going to focus on how we explain it. So, shear thickness expansions. Okay, so first though, I want to gather the phenomena. I want to tell you what it is that a theory should try to explain. Shear thickness expansions are liquids that solidify at large stresses, hence the title. Oobleck. If you go to in a popular science web pages and many science fairs and all kinds of events, school lecture talks, which I give myself, Oobleck has become the word for this material. This is cornstarch in water here. I'm just about to show you what it does. Based apparently on this remarkable book by Dr. Seuss. So, in which the world is apparently invaded by non-Newtonian fluid. I've not read this book, I'm afraid. I'm sure many of you have, but it's sort of sounds a rather surreal nightmare. Anyway, let me show you some. So, what we have here is cornstarch suspension. So you can go by cornstarch, and custard powder is the same as cornstarch, it's just has yellow dye in it and some sugar. Hence, bulletproof custard. I could have said bulletproof cornstarch, but that would be an even weirder title. So I'm going to drop this stick in here. So the idea is that this is a fluid if I'm very gentle. So I'm barely touching this, and I can move the stick around. You can see I can wobble it. And it looks pretty runny, maybe a bit sticky. But then it's difficult getting the stick out. Let's try this. Okay, so this is an unusual fluid. I've actually smashed the beaker here, and it's not leaking out. But and this now you can also see this is gone in. Okay, so it's doing what I said in the title. If you're gentle with this, it's quite constant with it. It just resists. So as somebody who recently, for the first time, became the owner of a dog owners will know what it's like to have a dog that has a different view of where you're going on your walk from you. It doesn't matter. The harder you pull it, the slower it goes. So this is really the same. So let's be gentle. I'll try to be gentle with this first. But even now, you see. Good. Let's leave that. Let's see what happens. So this may fall off at some point. Having already broken the beaker, I should play too much. So you see there's lots of very interesting flow instabilities here. So what's happening then is that the fact that this is harder to flow when you push it hard has a bunch of phenomena associated with it. One is that the transition from being easy to flow to being hard to flow can be very sudden, and the other is that the resulting flow can be very unstable. And if you see how wobbly the front of this kind of sheet of cornstarch is here, this is not like the flow of any Newtonian fluid. Even if I slow down the movie, you just don't get this kind of instability. So let me see if this will stay without falling off. I'll try and do that a little bit longer. It's going to fall off eventually. Right. How are we doing? Ooh, what's that? Oh, I see. Yeah, well, I want to go back to my slides now, right? Oh, thank you. Yeah, so you can place your bets as to when that's going to fall off during my talk and scatter bits of wet glue all over me. Okay, so this is the Daily Mail, one of the UK's most reputable newspapers. Talking a few years back there is sound on this movie. That's good, isn't it? There's sound on this movie, but I don't know what expletives that guy is uttering in his own language, so it's quite lucky that it is muted, in fact. And let's just see that again. So the first guy, you can see the whole movie, including this guy falling, sinking in, which is just like the Hammer did. He just stood still for a while and sank. And if you don't stand still, you can run across the top. See, that's still going up there. So this is the, well, and this is now, look at the logarithmic axes here. This is the stress as a function of strain rate for a shear thickening suspension, of which this is an example, although that's not exactly the one in the picture here. And you can see that at a certain rate of strain, if I above a certain stress, it's now 10 Pascal, certain rate of strain, there's 2 orders of magnitude jump in the stress. So a huge leap in viscosity. And what's more, there's hysteresis. In other words, you go up on the right-hand red arrow here, and then if you back off, so slow things down again, you come at a slightly higher stress and come back down a different curve. So that's a signature of certain kinds of physics that I will indicate in a minute, hysteresis. And if you look more closely at data like this, so this is actually data from this year from the group in Edinburgh that I'm still associated with and used to be in. So these are a bunch of flow curves, again stress against rate of strain on logarithmic axes, and what you're doing here to go from one curve to the other is you're changing the concentration. And this actually is cornstarch, it's just like that. So that stuff there is probably about where the blue curve is. So there's a parameter which is the concentration. So the dimensionless measure of concentration is actually the volume occupied by the solid particles, a fraction of the volume of space in this solution that's occupied by solid. So number per unit volume times 4/3 pi r cubed if they're spherical, which of course cornstarch is not exactly spherical, but we know how to correct for that. So this is a dimensionless number. It's important that it's dimensionless, but it's the control parameter which takes you from one flow curve to another. What you also find, though, when you look at this more closely, is that in these very vertical curves here, like the blue one, the flow is not there yet. Now, I actually going to... Okay. So now I'm afraid I have to issue advice to the cleaners, and I'm sorry about this. There's puddles of this all over the carpet, but you just have to wait for it to completely dry, and then you vacuum it up. I'm sorry, I wasn't planning that quite that way. Okay, so right, yeah. So the flow has structure. It's not steady. So, for instance, if I take somewhere in the middle of this, in other words, if I take a sample like that one and I put it in a professional flow measuring device, which is called a rheometer, so I have a carefully designed machine with moving parts that I can measure the stress as a function of time, I get a curve like the thing on the left. So a ordinary Newtonian fluid, that would just be flatlining in time. It obviously has a stress that is proportional to the rate, but if the rate's held constant, the stress is not wobbling around like that. So that's another characteristic feature, and it's also what we saw or related to this phenomenon here. So to say a little bit more about the movie, the red bars here are showing you the connections between particles and the forces that are carried between them. So in a computer simulation you can figure all that out. You can't measure it directly in an experiment, but you see what you have there is a network of forces which is coming and going, and you slow up and speed down according as to how well connected is the structure. So that brings me to the explanation of what's going on. My computer says 1 hour, 36 minutes and 10 seconds have elapsed since the start of the talk. So this is a disadvantage of having it set up too far ahead. I shall switch to my watch. Right. So how do we explain this? Well, there is a phenomenological behavior in terms of the stress as a function of rate of strain, which, if only we could explain that, would explain this. So let me say what I mean. Here is a viscous fluid. These are called the flow curve. S of R is a flow curve, and for a Newtonian fluid, it's a straight line. and I'm just increasing the concentration. If, as a function of concentration, I could get the following evolution of my flow curves, then everything you've seen would be explained. And this is increasing concentration here. If I could get the flow curves only to do this, then everything would be fine. And the reason is that these decreasing parts of the flow curve are mechanically unstable. So when you enter this kind of region of parameter space of stress or strain rate, you expect flow instabilities, and you also expect sudden stress jumps for this reason. Oh, so let me do the instabilities first. So the dotted part of the curve here is unstable just for the same reason as a particle at the top of a potential is unstable. This will just split off to either one side or the other if I work at fixed rate of strain here. And you can think about the acceleration of a small piece of fluid in a regime where the stress is decreasing with strain rate. You can see that it's got a positive feedback and will run away in one direction or another. So the flow instabilities one can understand from the negative slope regions of these flow curves, and the hysteresis likewise. If I gradually increase my stress, or rather if I increase the rate of strain here, then at some point I can't go any further on this lower part of the curve, and this is all unstable, so I end up jumping discontinuously to the upper branch here. And again, these can be two orders or three orders of magnitude apart in stress. And then if I come down, I can experience a hysteresis loop which comes down to this back kink here. So that's all fine. In other words, we know exactly what the target is for our theory. It's flow curves which look like that one, or particularly the whole family that I described before. So let me explain why that poses a difficulty. So here's what we want to explain. Flow curves of this type, let's just take a typical one out of the middle. So all we need is a flow curve with a wiggle. Now, however, if there's going to be a wiggle, and I'm going to have a theory of it, I have to be able to tell you where the wiggle is. So if we think about dimensions, stress, oops, go back, mass per unit length time to minus 2. So mass length of time into the stress has the same dimensions as pressure. The strain rate is the rate of change of an angle, essentially, so that's got dimensions of 1 over time. So I have to somehow find some physics that fixes one of these parameters. And the problem is that if we turn to our standard model of dense suspensions, which is this microscopic ping-pong ball model, it turns out I can't do that. So let me just explain what the problem is in those terms. The solvent has a viscosity. So that has dimensions that we know. It's 1 factor of time times the dimensions of the stress. We know, however, as those of you familiar with fluid flow of any kind will understand from what I've been showing over there, that inertia isn't relevant at the microscopic scale here. In other words, the fact that these particles have mass is not important. The fluid has mass, the particle density and the fluid density are almost the same. This is not to do with accelerations. The whole of the flow of these dense suspensions is to do with the fact that particles are slowly pushing fluid around. It's all overdamped in that sense. So there isn't a mass coming from the particles either. They do have a size, call that big R, and they have some force between them, which in the standard model is basically a hardcore interaction. So the force is 0 until the particles touch, and then it goes straight to infinity. So that's the kind of simplification that theoretical physicists like to make. And in this field of suspension physics, that has got us a very long way. So 50 years of progress are based on that sort of model. But in this particular context, we have a problem. Houston. If I look at this, I can get a length from the particle size, but I cannot get a time. And I look at that force curve, again, length from the fact that it sets in at 2r, but it's either 0 or infinity. So there's no scale connected with that either. So what I can't do is find a time scale which I would need to convert the solvent viscosity into a characteristic stress, S star. So I cannot, from this physics, I cannot make a characteristic stress or a characteristic strain rate, because that, again, requires the inverse of a time. So from the particle size, the fact that they're hardcore interactions, and the fact that they're in a solvent of viscosity nu s cannot give me a wiggle, because there's no physics there, dimensionally, that can present a characteristic value of stress or strain rate to me. So that's a kind of slightly subtle argument, and it sounds like there must be a loophole. Well, of course there is a loophole, otherwise I wouldn't be able to go on with the talk, but it's a subtle loophole. So the question is, which of those assumptions has to go, essentially? Something will have to. But meanwhile, let's just recap that. Standard model, then, we have a system where if I have strictly hard particles in a solvent, then depending on the concentration of those particles, I can have a low viscosity at low concentration, or a very high viscosity at higher concentration. Or in fact, if I push the concentration too high, the viscosity can diverge, and then I have a solid. But nonetheless, what I have in the Standard Model is either a perfectly Newtonian curve with a certain slope, or in the case where that slope is infinite, I have a solid. What I can't have is a wiggle, or anything which jumps discontinuously from flowable to jammed behavior. It's either always flowable or it's always jammed. So that doesn't explain any of the phenomena I showed you. So nu is the viscosity of the suspension as a function of concentration, and it has the potential to diverge at a characteristic concentration